What goes up can come down, but it's the middle of the rise that we're talking about. Ends closed, don't reach infinity. It hits everything between the low and the high. Continuity, intermediate value theorem. Don't forget to mention that continuous function, yeah.
It's the intermediate value theorem. I'm so excited! Warning. The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the end of the section on continuity in a standard Calculus 1 course, also known as differential calculus. And all of these sections usually end with the intermediate value theorem. Probably, again, as I say here, the coolest use of continuity. So what is the intermediate value theorem? Pretty darn easy to understand, honestly. Suppose that you have a continuous function on a closed interval a to b. You know what? I'm going to draw one. So here we go. We have some continuous function starting at x equals a, ending at x equals b. I'm just going to go ahead and mark that. Great. That sure does look like a continuous function from a to b on a closed interval. Great. And let n be any number between f of a and f of b. Now, the way I've drawn this, I've drawn that a comma f of a lies below the point b comma f of b. You should know that it could be that f of b is below f of a. It doesn't really matter if this function's rising or falling or whatever, okay? But we're going to let n be some number between the height at a and the function height or the function value at b. So that's what n is. And guess what this theorem tells us? Well, there must exist some number c on the interval from a to b such that f of c is equal to n. What does that mean? Well, since the function was continuous, there must be some point between a height of f of a and a height of f of b where the x value at that point leads to the height of n. So maybe I should say it differently. There is some point between a and b, we're going to call that c here, such that f of c is between f of a and f of b, and f of c is equal to n. This basically means that our function will attain every height between f of a and f of b on the interval from x equals a to x equals b. That should totally make sense, because if I tell you, I had to draw a curve, it started at a height of, let's say it started at a height of 27 and it ended at a height of, let's just say that's a height of 12. Man, and my curve was continuous. I sure hope I hit a height of 20. Well, if it's a continuous curve, it definitely hit a height of 20 at some point. That's just how it works. If it didn't, then there's something wrong with continuity. As I state right here, the proof of this is a bit much for a Calc 1 course. This is like an easy theorem to know, very difficult theorem to prove. Now, before we go into examples, it's interesting to note that a function which satisfies the results of the intermediate value theorem, which we call the IVT, need not be continuous. For example, and I'm not going to use that example actually, I'm just going to use an example off the side. You could have a function that starts high, ends low, but it doesn't need to hit a value in between if it's not continuous. And that's basically what I'm saying there. So how is it useful? Well, often in mathematics, we're more concerned that an equation has a solution than what the solution is. And in this case, the intermediate value theorem is incredibly useful in letting us know that an equation has a solution. Not necessarily what the value of that solution is, but that it has a solution. For example, use the intermediate value theorem to show that there is a root of the given equation in the specified interval. So the equation is e to the x equals 3 minus 2x, and the interval 0 to 1. Everybody has a different way of doing this. I personally love to move everything to one side. If this equation is true, then the equation down below, e to the x minus 3 plus 2x equals 0, is also true. They're the same equations. One's just manipulated from the other. But I like to work with the second equation. It's a little bit easier to work with. And here's why. I'm going to let f of x equal e to the x minus 3 plus 2x. And my question is, does this function hit the x-axis? I don't care where, I just care, does it? Does it hit the x-axis? In this case, they actually gave us a wonderful hint. They're saying that function would hit the x-axis somewhere between 0 and 1. So the first thing we need to do to be able to use the intermediate value theorem, we need to state that our function is continuous on the closed interval from 0 to 1. That's critical. If you don't do that, then you really have kind of destroyed the theorem. You have to showcase it's continuous on that closed interval. It has to be a closed interval too, by the way. So let's go ahead and first consider the closed intervals from 0 to 1. Now, all I need to do is showcase that this function is continuous, and I'm almost completely done with the intermediate value theorem. And the fun part of this is we know that our standard functions like exponentials and polynomials are continuous on their domains. So I just need to state to the world that e to the x and the polynomial negative 3 plus 2x are both continuous on 0 to 1. And it is literally that easy. That is such an easy statement to make because we know we have that theorem that says all our standard functions are continuous on their domains. So if you don't state that when you're using the intermediate value theorem, then you're completely wrong. You have to state that your base functions there are continuous on whatever interval you're considering. Whether you can even say in this case, they're just continuous on the real number line. That's absolutely fine as well. But now we have one of the conditions met for using the intermediate value theorem. In fact, we have two of them, closed interval and a continuous function. Now all I need to do is, well, to determine that this function hits the x-axis, I would love to show it that this function is negative at some point and positive at a different point. Because if a function goes from negative to positive, and if the function's continuous, well then it had to cross the x-axis. It's that simple, folks. So let's go ahead and do it. I'm going to look at f evaluated at the left edge point. Well, that's just going to be, let's see, e to the 0th minus 3, or in other words, negative 2. That's definitely less than 0. And f evaluated at the right edge point, well, that's e to the 1st, let's see, minus 3 plus 2. And you might say, well, how do I know that this is greater than 0? Well, e is 2.718281828. I think it's 459045. So if it's 2.7 and change and you subtract 1, you're still positive. So let's see, we had a function that at 0 started below the x-axis, and at time 1 ended above the x-axis, and our function was continuous. Therefore, the function must have crossed the x-axis. For some, maybe I should put it this way, f of c is equal to 0 for some c in the interval from 0 to 1. I'm not including 0, I'm not including 1 because, well, we know it's negative at 0 and positive at 1. So it's somewhere between 0 and 1, not including those edges. Now, the fact that our function becomes 0 for some point between 0 and 1 means that this equation has some solution between 0 and 1, which also means that this equation has a solution at some point between 0 and 1. Again, super duper important that you do two things. Have a closed interval. Actually, that's not even that important, to be honest with you. But let's just make sure that we have a closed interval, please. And that you make sure you state to the world your function is continuous. Then you just need to show your function's less than 0 at some point, greater than 0 at another point. Somewhere in between, it crosses the x-axis. Super nice theorem, one of my favorites. So much so, I want to use it again. So, is there a number that is exactly one more than its cube? I don't know. Is there a number that is exactly one more than its cube? That is a good question. I wish I had a way of knowing that there was a solution to that equation. Man, and I wish that I could rewrite that equation like this. But I don't know. Does algebra work? I think so. So now what I'm going to do is trade that equation out for working with a function. Well, maybe I shouldn't say this implies. I will just say let f of n equal n cubed minus n plus 1. And all I want to know is there a root? That is there a point where it hits the x-axis, or in this case, the n-axis? Well, would be great if I had a way of doing it. Notice that they did not give me an interval to work with. And that is usually the case when it comes to my exams for my students, is that I just hand them something and I say, I wonder if there's a solution to this. Use some method from this class to state that there is a solution to this. And so that is their clue that they're going to use the intermediate value theorem. So they go to here and they say, is there a root? Is there a way that this will ever become 0? Well, the first thing you need to do is note f is a polynomial. So, well, it's continuous on all real numbers. For all real numbers, it's continuous. Remember, you need two conditions: continuity, and then some interval, some closed interval. And this closed interval, you're going to actually spend a little bit of time trying to create that. You need to find a point where the function is negative and a point where the function is positive. So for me, I'm going to just check out f of 0. It's either positive or negative, so I get a win in that situation. Great, I have a positive value. Now, think of a number that you could plug into that function that would force it to be negative, like f of negative 2. That'd be a negative 8. Plus 2 plus 1. Still, that is, I was just going to say what it was. I might as well. You don't have to. But that's negative. Yay. Between 0 and negative 2, or set in the proper order from negative 2 to 0, it switches signs. So on negative 2 to 0, f has a root. And I didn't say this in the last example, but I should have, by the IVT, by the intermediate value theorem. In fact, for shame that I did not say that in the last example, I will go back to do that, but let's finish this one out. So let's see, I stated that my function's continuous. I showed that it goes from a positive to a negative value, or actually from negative to positive, but it doesn't really matter. So that on that closed interval from negative 2 to 0, f has a root by the intermediate value theorem. And to be very honest with you, you don't even include the endpoints on that. It's on the open interval from negative 2 to 0 that f will have a root. You don't include the endpoints because, again, the endpoints are where the function's either negative or positive, so you've already done that. Since f has a root, there is a place where f becomes 0, which means there's a solution to this equation, which means there's a solution to that equation. So, yes, there is a number that is exactly one more than its cube. And in fact, that number is somewhere between negative 2 and 0. Pretty cool. So I hope that is cool for you. Let's go ahead and go back here and just say by the IVT, because that bothers me that I didn't do that. You will have to state that for your instructor on an exam. You definitely want to state what theorem you're using here. So let's look at a use of the IVT. The atmosphere's concentration of carbon dioxide has been rising precipitously over the past 50 years. On the other hand, we know that in the past, the CO2 levels have been both higher and lower than they are today. What does the IVT tell us about our current situation? Well, let's go ahead and just plot. You don't need to be super accurate, but let's just pretend that here is our CO2 levels as of today. In the past, they've been higher. I'll use different color. They've been higher and they've been lower in the past. Well, what can you say about this situation? The CO2 levels on our planet fluctuate continuously. In other words, they don't drastically jump on a per second basis. They fluctuate continuously. So it's a very smooth fluctuation in CO2 levels. They don't just jump from, let's say, 20 to 100 within a second. It just doesn't work like that. There's a smooth fluctuation. So this, if you draw a function that represents the CO2 levels over the years, it might look, I'm just saying, like this. So what does that mean? Well, it means since it was lower than where we are today and higher than we are today, there must be a point in the past that had our same CO2 levels. That is, there must be a point in history where the CO2 levels match those of today. There's a lot of cool uses of the intermediate value theorem, but really, I mean, I've given you all the tools in such a short video, but there's not much you really can say about the IVT more than what I just have. So I hope that you enjoyed this video, and I hope you can feel the excitement. I love this stuff.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.